Hello YouTube viewers, welcome to my show Science Thursday. In today's episode we're gonna continue our robotics series, and today we're gonna talk about motors for robots. So let's dive right into it. So first thing that should come to your mind is why we are talking about motors when everything you require in a robotics is generally a linear motion. Basically, you may be thinking about like JCB is a hydraulic system, pneumatic system if you have seen it somewhere else. So why the hell we generally talk about motors rather than these two puppies? Well, core reason is efficiency. Basically, think of it this way: you have a robot that's supposed to do 100 kilowatt of mechanical work. Basically, take one object here, put it somewhere there. That takes a physical amount of energy, like mechanical energy, and it needs, let's say, 100 kilowatt. Okay, awesome. Here's the motor will consume only a little bit more. Basically, if you have to get let's say 100 kilowatt output, you can pump in 120 kilowatt. So basically the conversion efficiency from electrical energy to mechanical energy is very high. Now again, if a motor is just a dumb motor in only all it has to do is keep spinning, then the efficiency would be around 98%. But generally these motors have to have like braking system, precision control and all that. So due to those the efficiency is low, but even in those scenarios they are far more efficient than these two puppies. And then we are talking about high performance. When I'm talking about performance, I mean like when you are designing this, you get the control of it. Basically you're like, okay, this is a motor, it's supposed to do 1 ton, it will do 1 ton, because you have to understand it this way. If you are talking about hydraulics, they are the most powerful system out there. However, they suffer from slow basically there is a lag between this. Like if your robotic arms gets a command, hey, move 1 centimeter left, this has more than enough power to do that. This is like, I got this. Like you put 10 ton on this, like I got this, but it will take time. It will take its sweet time. So it is very slow, and it's also not very precise, very clunky. It's kind of like you have to do lot of gear reduction with this puppy to get a precision control. However, when you are talking about something like, let's say, pneumatic systems, they are fudgy by nature. Like you have to open the valve and you will close the valve once it reaches the open position. So by default, by definition, depending on your air pressure, depending on the system circumstances, temperature and all that, they are very fudgy by nature and not very strong. So again, there are uses for this. There are, like, you can't run a basically JCB using this puppy. You have to utilize that, and you can't have a cheap system using this. You have to use this. This is cheaper. So there are reasons to use these things, but most of the time we rely on motor because we get the performance and the efficiency. So basically you can have an entire factory running on basically electrical motors, and your power bill won't be like, hey, build your own nuclear power plant. So that's a very interesting thing. Now if you open the motor, go inside the motor, basically rotor and stator and all that, you get precision control on them also. Now that is very critical. Think of it this way: somebody says, hey, this is a robot and it has multiple joints. It has joints. Okay, awesome. But this joint only has to do, let's say, this, something like this. Only it has to move, let's say, 45 degree. So by designing the motor itself, you can say, hey, design the rotor in such a way that it gives me maximum torque but very minimal RPM. So you don't have to do a lot of gear reduction. You can do that. Now there are some scenarios where, let's say, you have an end effector and it spins around a lot for some reason. Let's say it has to do a lot of flipping things and all that. Okay, awesome. Then you can ask the engineer, hey, design the rotor or stator in such a way that I get the maximum RPM output. So I'm talking about like going inside and fine-tuning these puppies, and you will get much larger range compared to any of these things. Now again, you can of course control this like speed, thrust and all that, and again here also. But compared to this, yeah, these are like you are using sword, and this is like precision scalpel. So that is why you utilize motor, because it covers a lot of things, basically from speed, efficiency to precision control on the equipment itself. So that is why you utilize motor most of the time. Then the first thing, the moment you type robotics and all that, the first thing you will come across is stepper motor. So what the heck is this stepper motor? Well, is in terms of electrical system, it's a very simple brushless DC electrical motor. So there are no brush, there is no sparking thing, nothing. So it's kind of awesome, and that is necessary. If you want to build a robot that works for 10 years, 20 years, you have to make sure you're not using something that is inherently gonna wear out. So brushless DC electrical motor. So that's awesome. Now, why do people call it step? Well, basically if you open the motor, you will see the rotor and the stator, both of them have tooth. Now this tooth is designed in a very specific way. So the idea is that these tooth points basically pinches the magnetic field. Now due to the magnetic field, their magnetic field is not smooth. Now whenever we design normal motor, let's say water pump motor or a motor for your car, we design in such a way that is very smooth, spinning like spin as freely as possible. Here we want completely opposite of that. So these inherently makes it difficult. So the magnetic flux would be like my fingers and it will like align to it. So then what we do is, in the basically basically rotor department, we have tooth and we split it half and rotate it. Now you're like, why the heck we do that? Basically that forces one of the teeth will always be misaligned. So one of the teeth will be going backward, another teeth will be going backward in the same rotor. That is why it cannot freely spin. Again, depending on your electronic drive circuit, you can get the continuous spinning out of it, but that's not the desired output. Whenever somebody is designing this, the desired output is like, hey, spin 1 degree left, spin 1 degree right, or instead of left or right, they will say 1 degree clockwise, 1 degree anti-clockwise. Because of there are tooth nature, by inherent, like in terms of electromagnetic nature itself, it will always go in step by step. That is why we call it stepping motor, because of these teeth. This is the inherent nature. They are not, it's not meant to do free spinning. It's not your air conditioner or PC fan meter. It's by design meant to be like tuk 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 tuk. Now again, driving this is also very complicated. You cannot just connect it to a DC power source and be like YOLO. You have to drive it with ludicrously complex system. So you will have a wave drive technology. Sometimes people use full step drives. So basically, okay, one step. Sometimes people do half step because steps have a resolution. So generally you will have 1 step to 1 degree. Just going. So basically you have 360 degree, and each time you send an electrical pulse, tick, it will go 1 degree. But what if you want something, let's say you are doing 3D printer and you want your basically rotation to be less than that, let's say half a degree. To get that half a degree, people will do half step. Basically they will send one command to move forward, another command to move backward. So while it will be fighting, it will get stuck in half the position. Basically instead of going 1 degree full forward, it will go only half a degree. Then you have micro stepping, where you will get even more resolution, but side effect will be, because you can see it becomes more or less like a sine wave. So at that point you will not have too much torque. So this is very good for, let's say, 3D printing. But if you want to run a CNC machine, people will generally say, hey, stay at like half step. Again, good electronics, good circuit with a good margin of error and all that, you can easily use whatever you want. Micro stepping for CNC also is possible. It's just, that's up to you. You have to understand the tooth nature is by design made in a such a way that it will always stuck. So benefit of this, it can be open loop. Basically you simply say rotate 10 degree clockwise, it will do that. You can send after that, hey, rotate 5 degree counterclockwise, it will do that. You don't have to count it. You don't have to like, did you do that? Did you do that? Again, depending, as long as you are inside the design tolerances. So let's say this motor is designed for, let's say, few grams of end effector. Basically whatever, the print head is like few grams and it's like everything is cool. But let's say you put something too heavy, let's say a CNC machine, or CNC machine was designed for cutting wood and you put aluminum in, right? The resistance would be so high, it will start missing steps. Basically it will slip and you won't know. So you can send a command. Basically your software will send a command, hey, move 10 degree. But it would have only moved 5 degree because they're of the resistance. But then after that you send a command, let's say move backward to 20, you have missed the step because there is no feedback into it. These are generally used for open system. So again, designing is very critical. You must design it properly, and this is what your printers have. I am talking paper printers, I am talking laser printer, inkjet printer. This is what they are relying on, because the paper is not that heavy and the motors are overbuilt. Let's say it takes 1 gram of torque, they will put 3 grams of torque just to make sure that they never miss. So this is the technology of stepper motors. Teeth, electronic drive equals steps. Then you come the most ill-defined topic out there, servo motors. Now this is the one thing you will hear unilaterally told to you is like stepper motor is for children, servo motors are for grown-ups. And it is true. Servo, like you cannot go into an industry and say, hey, I want to build a robotic arm with stepper motor. They will like, there's a door, get out. So what the heck servo motor means? Well, first thing you have to understand, servo motor is not a motor type. Basically whenever you are talking about stepper motor, you are talking about exact motor type. When you are talking about servo motor, you are not talking like that. You are talking about a class of motor. Like this type of motor is not there. This is like this category of motor. So what this category means, category simply means closed loop system. Stepper motor is designed in such a way that whatever your system you are doing, it's like I'm gonna keep count myself, like, hey, computer send me 10 commands, I'm gonna follow those 10 commands. Here it's a closed loop system. Basically it double checks. So let's say you send a command, spin the shaft 20 times. There will be an encoder that will be counting it. It's like, okay, I got the computer command 20, hey, you missed it, whatever. Let's say the torque was not enough, the power fluctuation, whatever have you, or the load was high, the electrical pulse missed it, so it's like, hey, I only spun up 19 times. The encoder will send an alert to logic board, and logic board will be like, okay, I got this. It will halt any further pressure. It's like, hey, spin up one more time. Okay, awesome. Then it will follow the further command. So there is a feedback loop. There is a what we call closed loop. It's not open system. It's not like, okay, I told you, you did it. No, they double check it. That's the reason. This is what we call servo motor. There is always a double basically checking. Now generally for industrial purposes, they are also brushless. So what kind of brushless motor? Again, depending on the design, sometimes it's our AC brushless motor, sometimes it's basically DC brushless motor, because permanent magnet generally have higher torque. So again, depending on you design requirements, you can have any type. Generally it's brushless for longevity reasons. So, and whenever you are talking about basically servo motor, you are talking about three core things. You are talking about the motor, obviously, then you are talking about the encoder, the feedback mechanism, and then you are talking about the logic. These three are all together combined makes what we call servo motor. You cannot just say, hey, motor is a servo motor. No. Do you have the encoder? Okay. Do you have the logic to drive it? Because let's say you put you have your normal 3D printer and you just connected the encoder. Again, the encoder must talk back to the software and tell the software, hey, the motor has missed a step, send an extra signal, because you have to understand there is a logic feedback going back and forth. So due to that reason, these things are generally sold as a package. Even if you are buying, let's say, a servo motor, they will like, okay, this is the motor, this is the driver circuit, this is the logic board. All three would be sold to you as one unit. So, and generally most people are familiar with cheap servos are like this. These are not free spinning servos. These are like they have limitation with rotation, so they cannot just keep continuously spinning. Benefit of that, they generally have a potentiometer connected to their output, and the potentiometer has a limited range. So utilizing that range, it has feedback. It's like, okay, the potentiometer generally acts as a voltage divider. So let's say the voltage from 0 to 5 volt, 5 volt is like it has reached maximum position, 0 volt is minimum position. Somewhere in the 50%, you're like, okay, the volt, it will keep sending command, and as long as it will, like, the rod will keep spinning. So the moment the voltage on the potentiometer reaches 2.5 volt, it's like, okay, done, signal set, because it's a closed loop. You have to understand, this is a closed loop. All the circuitry, all the H bridge and all that is needed for driving this is in this. That is why you simply buy this and you get a like command sheet how to talk to it, because it's doing all the three things. It has the motor, it has the encoder, and it has the logic built into it. And here people generally use brushed DC motor, it's cheaper. So that's the whole idea. Servo motor is a class of motor, not a motor type. Then you generally employ for practical purposes brushless system, and all three systems must be working properly with each other, otherwise you just have a junk. And you can find, there are places and there are companies that manufacture stepper motor servo system, and it also has multiple advantages, because stepper motor rarely slips or any does things. People just use a stepper servo motors, and it has become very popular in high-end CNC, specifically with wood, because if you have something servo motor system in CNC wood, you can get very smooth finish, because it will never miss a step. It will like, okay, it's supposed to go there, I will make it there. So people get very good output with that. Then we are talking about the ugly part, about the oily, the messy part, the gearbox, because generally you have to understand, whenever you are talking about robotic arm, the robotic arm is not supposed to do like this. There's generally a very methodic reason. It's like, okay, take the object here, take it here, drop it here, take the object here, take it, do it here, do this. So generally, to have that methodic nature, we need more control. Basically, motor, even with a stepper motor, you still have a control, like, okay, spin 360 degree and you can divide it to, like, how many degrees you have. That's not enough. To get enough, basically what we do is basically introduce what we classify as step down gear system. So benefit of that is, instead of counting, hey, you have rotated like 45 degree and all that, you have to rotate like 10 times. It gives you much more range for control. It's like, okay, 10 times, rotate 10 times, rather than like one. You're like, okay, you have the time, you're like, okay, it's at 9.5, it's supposed to be at 10. The electronics will start to reduce the power, so you're like, okay, exactly at 10 it will stop. So that it gives much more control. It's like expands your system. It's like, okay, instead of 10 pulse, now you have to control with 100 pulse. So it's much easier to control 100 pulse than 10 pulse, basically, because if you miss 1 pulse in a 10 system, you have 1 by 10 fault. If you are missing, let's say, if you have ludicrously high gear reduction, you can be like, hey, I missed one pulse in 10,000 system. So then it will like, 1 in 10,000 accuracy. So that is why we generally want gear down. Like it expands your system. So your fault, again, unless you have designed it ludicrously stupid, your fault will be within the region. Then reduced speed is also, everything is better if you have lower speed. Why? Simply because everything will wear down less. Basically, if your robot is going YOLO, it will wear down. I am talking about the bearings, I am talking about the everything, every grease seal, everything will wear down quickly. So reduced speed is also awesome for that. And increases torque. That is what is the reason why we can have a robot that is like only consuming few kilowatts and it can freaking lift a car. Like it can literally, yeah, here's a car, here's a lifted, here's a rotated car, here's a underside, so you can weld on the top. I'm like, damn. Those are all things possible because of the gearbox. Then we come to the most neglected part, the brakes. Now brakes are there for safety reasons. Now I'm not talking about safety when I'm talking about like safety as in safety of human. Again, that's an added bonus, but the core reason of it is, think of this way. When you're moving something big, let's say a 2-ton car, and you're like, okay, lifting it and moving it. Again, generally it won't be 2-ton because at that time it will without the engine and all that. So let's say it's still a ton of object and you moved it. For some reason, malfunction happened. Let's say your robotics failed or electronics failed, something happened, things happen, and it's moving. But here's the deal. Unless you apply brake instantaneously, you are moving something that is 1 ton. It will go through any brick wall you have. It will like, you just made a projectile of 1 ton. Again, it won't be like, blasting, exploding buildings and all that, but it's still dangerous. To make sure all the all the serious robotics generally have a fail-safe braking system. Basically, everything must check out, only then the brake will be released. Brakes are basically like, if power goes up, brake will automatically apply. So for that reason, we always have braking systems. Like this is something must be there. This must be, brake must work even if there is power fault. Like generally that's the first requirement. It's like, hey, what happens if power fail? Brake automatically applies. Awesome. If you're like, hey, the electricity must be working in order to brake to work, they're like, yeah, get out. So safety reasons, obvious. Like, and there is like a lot of system with braking systems. So you can have a clutch braking system, you can have disc brake system, and you can have permanent magnet braking system. There's a lot of system. Like this is something you have to think about if you're building a serious robot. Then it also allows for power saving. I'm like, how the heck it allows for power saving? Think of this way. Let's say you are using a stepper motor and you're like, hey, it has a holding torque. Okay, awesome. You lifted a car, let's say a car chassis up, and then other robots are doing the welding. Awesome. Here's the deal. For that while, like whilever you are holding the weight up, let's say 5 minutes or 1 minute, you are still expending electricity in order to hold that position. That's wasteful. So what generally they will do is apply the brake. The moment the position is reached, the brakes will be applied. So once you have the brake applied, the electrical motor can rest. It's like, I don't have to waste energy. And that also makes sure the motors don't overheat, because like, holding torque is not something that is very good for your health, for motor's health. So that it saves power. On top of that, with modern electronics, with modern development in IGBT technologies, we have regenerative braking. So what we'll do is like lifting 1 ton. Let's say you expended around 100 kilowatts of electricity. Okay, awesome. Now again, you're a robot and you're lifting something. That means you're gonna put it somewhere else. Okay, you moved it here and you're putting it down. Now while you're putting it down, generally the old system was they will slowly open and close the brake, open and close the brake, open and close the brake, or they will have the motor resisting it. So like instead of just dropping, it will like slowly go down. Here what we'll do is like, hey, all motor and generator is literally the same. Only thing you have to change is the wiring. So somebody figured it out. Hey, let's change the wiring in the control system. So that motor now acts as a generator, and because of the falling mass, you can extract energy out of it. You're like, okay. Now that has another benefit also. Not only you extracted the energy out of it, again, you're not going to extract like 100 kilowatt that you put into it. You're going to extract 30 to 40% of it. So that energy is there, because now the brakes don't have to fight as hard. Like brake is, instead of fighting let's say 1 ton falling, it's fighting something equivalent of let's say 100 kilo falling, because most of the energy has been taken out using the generator system. So that also saves money. And again, it's not that big of a deal if you have only one robot. Imagine a Toyota car factory where you have like 100 robots, each robot saving 30 to 40% electricity. Damn, that's like in every 6-7 months you can buy another robot. So that is also becoming a very critical thing. But again, you must have electronics that can support that, otherwise you're gonna roast your system. So brakes are also very important for safety reasons, for power saving, and again now even more power saving, so due to regenerative braking. I provide the video down below, you can check it out. So this was my presentation on why we utilize motors for robotic systems. I hope you liked it, learned from it. In that case, please click the like button. If you didn't like it, didn't enjoy it, I would urge you to press dislike, press it twice to show me your extra disappointment, and please leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.